So I will start by describing the desired system characteristics. Then I will dive a little bit deeper into specific scalability challenges. And I will also present the Google Cloud Storage architecture at a very high level. So what do we want from a cloud storage system? Ideally, we would like to achieve multiple goals at once, including reliability, durability, speed, low cost, simplicity, big data, global access from anywhere, atomic updates, and strong consistency. However, it's not realistic to attain all those goals at once because, for example, if you're talking about speed, one can try to build the entire storage stack on top of SSD, but this would be prohibitively expensive. So given a limited amount of SSD, we can put it to good use, using it as a caching layer, store recent data on SSD, or store metadata on SSD. So there are multiple interesting trade-offs to be considered when we build such a storage system. So we want to hide the complexity behind a very simple user-friendly API so that the entire magic will happen at the cloud, and from the user's point of view, things will just work. So the cloud storage can be, in an ideal world, viewed as a single local machine that is totally available at all times and has infinite disk. So that's more or less an idealistic goal. And we don't want to burden users with any kind of boilerplate code for the access, so the APIs should be very simple and intuitive to use. So the storage system has to deal with various failure modes. Many things can fail at different times. For example, we may run into network connectivity problems. Machines in the data centers themselves can fail. We can have bad config pushes or bad software updates. We need to route around those failures and build a fault-tolerant system that can hide those failures from the users and provide high availability. So for latency, we may need to move data as close to the user as possible. And for high availability, we want to replicate data to multiple data centers. So for data integrity, we need to identify and recover various data corruptions. At a very large scale, those corruptions that, however unlikely they are, they would always happen. We have to deal with hardware failures, software failures, and various combinations of those. So for infinite storage, we need to build capacity and have proper capacity planning, predictions, and to make this magic happen. So recently, Google launched an infinite storage service for photos, and it takes, behind the scenes, careful capacity planning. So for data durability, we use different error correction codes, and again, replication across cells with geodiversity that protects us against various disasters that can wipe out a single data center. And we need to run this service with monitoring, health tracking, and deal with various unavailability scenarios. Now, what kind of API model to use? There are like two basic models when we consider individual objects. The first one is base, which means eventual consistency. It scales very well. It provides cheap writes and reads. However, it makes client life much more complicated because reasoning about eventual consistency is very difficult. So another model is ACID, which is essentially strong consistency. It's much easier to deal with. It's fully predictable. It has causality order. However, it doesn't scale as well as eventual consistency because it sacrifices to a certain extent max QPS and latency. And I will elaborate a little bit deeper at a later stage which model we are using. So, what are the main scalability challenges we are facing? So, first of all, the corpus size is growing exponentially every year. And the average lifetime of a storage system is roughly 5 years. So after 5 years of evolutionary design, we need some kind of revolutionary redesign and deployment of a completely new system. So unfortunately, complexity is inherent in dynamically scalable architectures. So let me give you some examples of various scalability problems and potential solutions. So as you well know, the CAP theorem states that we can't achieve 3 of those objectives at the same time. That is consistency, high availability, and tolerance to network partitions. However, it's not all or nothing. We can do better. So for instance, if you have some global namespace, and we store the actual metadata in the regional partition, during the network disconnect, we can provide some degraded operational mode where updates would still be possible. So if this region gets disconnected from the network, so creation and deletion operations can be unavailable. However, updates in this region can be done based on the local access group. So this means that after this disconnect is repaired, we would recover from this outage and proceed normally. And so those kinds of trade-offs are very important for providing continuous service to the users without disruptions and graceful degradation when we face various sorts of failures. Okay. So another problem I wanted to talk about is hotspots and sharding of metadata. So when users pick the object names, if they end up being like in a sequential range, they may create hotspots, especially when we need to provide consistent listing. So if we were to come up with any static sharding scheme, it would also have its own scalability limits. It would scale linearly with the sharding factor. However, it would also result in inefficient listing because of a large fan-out factor. So a natural solution for those kinds of hotspotting problems is a dynamic sharding. When we have a hot range under load, we would keep splitting it, and vice versa. When we have a cold range that is splitted, we would merge it back. So another problem we are facing is metadata processing. So when we generate daily bills, if the system requires to go over the entire cold corpus, it doesn't scale well because even the metadata size is huge. So what can be done is just to do incremental billing. So if you were to take all recent object deletions and all recent object creations for the past billing cycle and keep the cold corpus billing as is, we can generate incremental billing. So this incremental billing will have complexity that is proportional to the churn rate rather than the corpus size. So it will scale much better. So another problem is isolation. How can we isolate between millions of cloud users? It's just not feasible to keep track of each of those users individually. No system can scale to that order of magnitude. So what we can do instead, we can focus on the top elephant users and put all tiny users in a joint bucket, so to without tracking them individually. So that's another example of how solving the scalability challenge as far as the total number of users we need to deal with. So now I would like to give you a brief overview of the Google's cloud storage architecture, and this is just like a fair to give you a flavor of how it's designed. Unfortunately, I can't go into too much into the details, and I don't even have time to do so. So Google has global data centers that have internet access, and they're all internally connected by a private backbone. So the production system is run by so-called site reliability engineers who are responsible for maintaining productions, and the dev teams are also deeply involved in production maintenance. So inside the cloud storage, we have like two main layers. One is the data service layer that deals with actual data replications, actual data bits. So this layer is responsible for replication and sharding, and it's using Colossus at the level of one single data center. So Colossus is a replacement of the first generation of Google file system. And as I mentioned, like every 5 years, a new system comes up because the old system outstretches its scalability limits. So the metadata service is a layer that maps user-specified object names to the addressable data references. And these layers provide low latency with high scalability, and it has limited ACID semantics, which makes it user-friendly as far as causality order. And it uses Spanner, which is a successor of Megastore, and I will talk a little bit about Spanner at the end of my presentation. So data replication poses many interesting optimization challenges. So we want the data to move as close to the user as possible, and this will reduce the application complexity. We need to deal with various legal requirements and restrictions. We need to optimize data moves, and we also have to think about costs, and some cost reduction methods includes deduplication of identical data chunks, adjusting replication for cold data, moving it to a cheaper cold storage, use different encodings, and also we make extensive use of caching, which reduces network bandwidth. So data replication is a continuous multi-criteria optimization problems that has to consider various failure modes when individual nodes and network links can fail or be unavailable just because of network bandwidth unavailability. So same is true for the availability of individual data centers. They may be overloaded and we may not have enough capacity for background replication traffic. So the high-level architecture of the data replication stack is that we have a centralized so-called location assignment daemon. So that's the replication brain. So it takes in the entire state of the universe, including state of individual data centers, where links and various other characteristics like the amount of available storage capacities in the data centers, etc., etc. And it talks to executors. So executors, that is bit pusher, the job that actually moves data around. And we have like the replication queuing logic, And the main objectives of this replication engine is to respond quickly to the changing environment, to prioritize work accordingly to internal objective functions, to maximize link utilization. We want to utilize troughs in the user-facing traffic for replication traffic. And also we want to minimize wastage, that is minimize abortion of any replications and build resumability logic into the system so that we can resume work that got terminated for whatever reason. So, so just a disclaimer, this is not the most recent generation of the system. It's constantly evolving, but it's close enough. So for metadata layer, we use Spanner. It's also planet scale storage system for structured data. It has a global location agnostic namespace, and one of the main features of Spanner is support of distributed cross-group transactions. We can transact between multiple rows in the database. So the replication is using Paxos, and it catches up very quickly, and Spanner provides high availability by failing over all client requests whenever necessary. So Spanner universe consists of multiple zones. Zones can be considered individual data centers. So each zone has a zone master, location proxy, and span servers. So span servers are the servers that process the actual transactions, and location proxy is used by clients to find the right span server to talk to. So the metadata replication is using Paxos groups, which can be customized and configured in for various topologies. So the span server is responsible for multiple tablets. Tablets are partitions, so Paxos groups. So they maintain internal mapping as a key value store. So values are the values for different columns in the database. And the data and logs are also stored in Colossus. So Paxos provides high availability at the expense of increased latency. When we commit to multiple quorum instances, the data is highly available immediately after write and can be served for reads. Now, I would like to conclude my talk with some useful principles for a scalable cloud storage design. So we want to build a system that can scale by multiple more orders of magnitude, assuming hyper-exponential growth if we wanted to survive for 5 years. So we want to make the system as adaptive as possible to traffic changes, and making that requires many subtle optimizations. We want to degrade gracefully in face of failures and build fault tolerance at all levels. And we want to support some data aggregation and incremental processing, for otherwise the sheer number of individual objects may overwhelm the system. And last but not least, we want to keep the complexity of the system at bay, because complexity creep is one of the main dangers that we face with cloud storage. Too many optimizations, too many complex layers interact in unpredictable ways, and real-time debugging and maintenance of those systems becomes very complicated. So, and there are some references and the link to the Google Cloud Storage. Thank you.